And we are back. All right, today we are going to talk about integrated rate laws. Last class we talked about just rate laws or differential rate laws, which we were showing how concentration affects rate. Here, with these integrated laws, we're showing how concentration and time affect rate. So we're going to go through each of the three orders we talked about last class: first order, zero order, and second order, and go over their rate laws and then their corresponding integrated rate laws. So for first order reactions, usually those are reactions involving a single reactant. So we would write their differential rate law as such. So rate equals K times some reactant A. So this would be the reaction here. So let's say A is our reactant, and then we're producing some amount of products. Okay, and then since this is first order, remember we're assuming this exponent is 1. We just don't have to write it because it is first order. And remember, this 1 doesn't necessarily correspond to this coefficient. This coefficient right here, it could be 1, it could be 2, 3, 4, or so on. Just remember the exponent doesn't necessarily have any relationship to the coefficients. The coefficients just tell us the mole ratio of the overall reaction. Okay, so that's the differential rate law, how rate depends on concentration of that reactant. Now for the integrated rate law, it shows us how concentration and time affect rate. So our integrated rate law for first order, we take the natural log, ln, of our concentration of A at some time t, K, and that's equal to negative K. K is still our rate constant. T is our time, normally given in seconds. And then the natural log of A sub 0, which is the initial concentration of A, the concentration of A when time is equal to 0. So for all of these integrated rate laws, what we can do to identify whether a reaction will be first order, second order, or zero order is to graph them. So for all these integrated rate laws, you can look at it in terms of y equals mx plus b. So if something is first order, you can plot the natural log of the concentration as your y-axis versus time. And if you do that, you will get a linear slope, and that linear slope will be negative k. So for example, if we have the following reaction, and the reaction is N2O5 decomposes into NO2 and oxygen, we're given, normally you would be given just concentration values of N2O5. Oops. And then what they're doing, taking the natural log of all that, plotting it, so that's on the y-axis versus the time on the x-axis. And if you look, the slope is equivalent to the negative of the rate constant. So for any first order reaction, the natural log of concentration versus time is a straight line. If you do this and you don't get a straight line, that means it cannot be first order. It has to be zero order or second order. Okay, so that's for the integrated rate law, how concentration and time affect the rate. And what we can do for all of these reactions is calculate the half-life, the time required for a reactant to reach half its original value. If you remember, we talked a little bit about this during our study of nuclear chemistry. So for first order reactions, this is the equation for half-life, and how we get this 0.693 value. Remember, half-life, it's half remaining, so here we'd be taking the natural log of 2, and that's 0.693. So you can either calculate for the half-life or calculate for the rate constant k if you're given the other one. So if you'll notice here, half-life for a first-order reaction is going to be constant. Half-life does not depend on the concentration of reactants. It's only dependent on k. So for example, let's say here, we want to calculate for k So we want to calculate for k if we're given the half-life. And normally you'll be given the half-life in seconds. However, you could be given it in minutes or hours. Just keep in mind that will affect your units of k. So if we rearrange the equation, the half-life equation, and solve for k, now it's k is equivalent to 0.693 over the half-life. So in this case, 0.693 over 20 minutes. So when we do that, we get a value of 0.0347, and then our units of k are simply inverse minutes. So units of k for first-order reactions are always inverse some value of time, whether it's inverse seconds or inverse minutes or inverse hours. Okay, then also we should be able to use the integrated rate law to solve when it's not necessarily a half-life. And this is a good graph showing you that for first-order reactions, every half-life here is constant. Every half-life here is 100 seconds. Okay. So now let's say we have a first-order reaction. It's telling us that. So now we know we use that integrated rate law. And it says it's 35% complete at the end of 55 minutes, and we want to know the value of k. So since it's 35% complete, we can't use the half-life equation. We need to use the integrated rate law. So the natural log of the concentration is equivalent to negative kt plus the natural log of the concentration at time 0. Okay, so here's where it's a little bit tricky. So if a reaction is 35% complete, you have to think about, okay, how much of this reactant A is left unreacted? So overall, for any reactant, there's always going to be 100% of it. So that means if this reaction is 35% complete, that means for A, there's 65% of it unreacted. So that means for our concentration of A here, 65% or 0.65. So here we use the natural log of that concentration, that percentage. We're trying to solve for K. We know our time here is 55 minutes. And then we have to think about, okay, what's the concentration at time 0? So originally, for this reaction, at time 0, 100% of A is unreacted. So converting that to a decimal, that means it's the natural log of 1. What